Greetings, Earthlings. Let's suppose you have an analog meter that you got somewhere that you know nothing about its specs, except that it has a range of 0 to 100 on its scale. How can you use it for something useful? Like, suppose we want to turn this into a voltmeter that measures up to 10 volts, let's say. So full scale will be 10 volts, that's 5 volts, and so on. Well, to do that, we need to know its resistance. Now, we can't just measure the resistance with a meter directly because they're very sensitive. We don't know what the full scale current value is. Typically on a meter like this, it could be anywhere from, 10 microamps to a milliamp, 5, 10 milliamps, whatever. And we don't know. And we don't know how much current, an ohm meter would put out. But what we can do if we have a variable voltage source and a known fixed resistor, there we go, that's a 0.1%, 10,000 ohm resistor, 10K. Okay. And so what we can do in that case is, first we have to sort of determine which is plus and which is minus. And that is not obvious. So we're going to guess. And we're going to be very careful when we apply power to make sure that we've got it right. So I've got this down at 0 right now. That's 0. And that's 0. There you go. So I'm going to turn that on. I'm going to turn it up very slowly, and hopefully the meter moves in this direction. If so, I've got it hooked up right. If not, okay, it does. If not, I would have had to swap the leads around. Okay. So now if I get it to full scale, that looks like full scale. Check the voltage. Okay, 1.86 volts is full scale. Now that is through both our known resistor and whatever resistance the meter has. So let's measure the voltage across just that resistor, and that will tell us how much current is flowing. Okay, 1.75. That's 1.75. This was 1.886. Okay. 1.86. 1.75. So 0.11 volts is full scale on this thing. Okay. But what we know is 1.75 volts through 10,000 ohms is what? 175 microamps full scale. So then what did we determine? There is 0.11 volts full scale. So 0.11 volts, just using Ohm's law again, divided by 175E minus 6 equals 629 ohms resistance for that meter. Okay, so now we said we wanted it to be 10 volts, right? So we can do the calculations. I'll put them up here on the screen. What we end up with is we have two resistors in series, and they form a voltage divider. And so we're going to put 10 volts in, okay? 10 volts divided by the total resistance is 175 microamps. This is simple stuff. RS equals 10 volts divided by 175 microamps minus 628. And that is about 56.5 K. Where am I going to find a 56.5 K resistor? Well, I might have something that's pretty darn close. Okay, here's a 49 point, this is as close as I can get, 49.9K. 6.65K, okay? So 49.9K in series with a, what did I say, 6.65K. Gets us pretty darn close. What I'm going to do is I'm going to clip those together here. Oops, I said I'm going to clip those together. Okay. And since I have this meter handy, I'll do a quick check. Oh, it's more than 20K. Duh. Okay. 56.6K. We want a 56.5. That's going to be close enough. All right. So we'll replace the 10K with the 56K. I'm going to turn that back down to nothing. And we should see, I'll go back to volts here. What else? Okay. Let's see if I can just hang these in here. Okay. All right. And we'll try this. Okay, I'm reading about 2 volts there. You know, we're at 20. Okay, and 2.07, that's pretty darn close. So let's go 5 volts. So I get it to 5 volts. That's pretty close. 5.12 over there. And full scale. Well, let me set it to 10 volts red on the orange meter there and see what it looks like. There you go, 10 volts. Pretty close to full scale. Tap, tap, and it's there. So, yeah. So that's now become a voltmeter. And if I had different resistors which I could switch in place of this one, I could have different ranges. I could go, you know, whatever. That's fine if we have a meter. Let's suppose we don't have a meter. And let's suppose we don't have a variable voltage source, okay? Let's suppose we're on Gilligan's Island, and you're the professor, and you've got a meter, and you've got Mrs. Howell's hearing aid battery, and I say that because that's a constant voltage source. So Gilligan's Island's from like the 60s, so that would have been a mercury battery, and that would be a constant 1.35 volts. I don't have one of those, but I do have this thing, and I can set that to, I can set that can stand in, as it were, for the mercury battery. And then, let's see. Okay, so I'm going to remove all this. Remove all this. And the other thing you have is a resistance decade box, because you do. Okay. So as I said, let's suppose you're the professor on Gilligan's Island, and you just happen to be carrying a resistance decade box with you because you were planning on doing some experiments on your 3-hour tour. So you've got Mrs. Howell's hearing aid battery, And you also have a box of random resistors somewhere to make this work. Oh no, this won't work. Well, I can make this work. Let's see. This is set at its highest resistance right now, which is 9,999 ohms, which is too low to do a proper job. But what I can do is this will still work if I set it, and that's, you see, having no effect. That's having no effect. Okay, here we go. What I'm going to do is set it to 75%, okay? And that is 9.8K. And now if I go to 100%, here we go. That's 7.2K. Okay, so here are the equations. 1.35 volts divided by 9.8K plus the resistance of the meter is 0.75 of the full-scale current of the meter. 1.35 volts divided by 7.2K plus the resistance of the meter is the full-scale current reading. Okay, so we'll substitute I in the second equation for I in the first equation. And that gives us 1.35 volts divided by 9.8K plus the resistance of the meter is 0.75 times 1.35 divided by 7.2K plus the resistance of the meter. Reducing that gives us 1.35 times 7.2K plus resistance of the meter equals 1.0125 times 9.8K plus the resistance of the meter. So we multiply that out. 9.72 plus 1.35 times the resistance of the meter equals 9.925 plus 1.0125 times the resistance of the meter. And subtracting to get the resistance on both resistance values on the same side, or a single resistance value on the same side. 0.3375 times the resistance of the meter equals 0.2025. And that says the resistance of the meter is 0.2025 divided by 0.3375, or 600 ohms. And that is basically what we measured the other way as well. We probably don't need to be much more accurate than that for our purposes. You know, the professor just wants to create a 9-volt battery to power the radio, because the radio they have an AM radio which they can pick up transmissions from Hawaii, of course, but it runs off a 9-volt battery, and so he has to fashion a 9-volt battery out of coconuts, seawater, zinc anodes from the minnow, and whatever else he can salvage. Yes, and with that bit of silliness, we'll move on.